Good morning, everybody. Welcome to our machine learning seminar. Today, we'll have a pleasure to have a presentation from Juan Esteban Suarez from the Department of Mathematics, Technical University of Dresden, Germany. And the title of the presentation is already on the screen. So not to waste more time, please, Juan, go ahead. The floor is yours.
Thank you very much. So hello, everyone. My name is Juan Esteban Suarez. I am part of the Center for Advanced System Understanding, that is an institute in Görlitz. And I'm also part of it was Balsarini group in CSBD in Dresden. And today I'm going to present variational formulation for solving non-smooth PDEs. So let's go. So first, a little bit of the motivational and the general setting. So in general, I'm interested in solving PDEs of this kind of form. So it could be some time dependencies that you have the time differential operator, and then you could have a spatial operator that could be linear, nonlinear, some boundary conditions, general. So I'm not restricted to any specific setting, but it's more like solving PDEs in general. But then instead of using like the standard methods, finite difference or finite elements, here we try to solve everything under a variational formulation. So what does it mean? That it is not trying to solve this in the setting of equation one. We formulate an energy functional, and then the idea is to find the function that minimizes this energy functional, right? So we consider two kinds of problems. The forward problem, in which we impose, for example, the Dirichlet boundary conditions, and then want to find the solution U that minimizes the loss of the PDE itself, that is here that you see here, and the loss of the boundary conditions. Or we are interested, for example, in the inverse problem setting, in which we also have the PDE constraint over the solution, but we want to infer, for example, a parameter lambda. So now the optimization is over two things: a function U and a parameter lambda. And then the idea that we can choose different kind of norms for different PDEs. As we will see maybe later, or I will tell you a little bit later, the main problem when trying to solve these variational self-constrained formulations is that the imbalances with the losses could make the optimization problem very difficult. So the fact that we can choose different norms for the different losses is a kind of an advantage. Okay. Now, so I will, in the whole talk, I will be giving first like the necessary tools for solving PDEs, smooth PDEs in particular. And then we will use all these tools to go into the setting when the solutions are not smooth. So for example, when we have discontinuities. And then just to motivate a little bit the difficulties that this kind of PDEs present, I just want to show you what happens when we have a discontinuity, like the orange plot here, and we want to just approximate it. Here, there's no any PDE involved. We just want to approximate the discontinuous function. So if we use a global polynomial to fit this orange function here, we will see this kind of oscillations. And this is called the Gibbs phenomena. And basically, the problem is that since the function is smooth, here you're trying to approximate like an infinite slope. So then the function will oscillate a lot, such that the transition in the discontinuity is, let's say, hard. So this is what happens if we just try to use naively the standard methods. And we will see now how can we exploit the variational formulation to overcome this issue. Okay, so now let's go a little bit to the gradient flow. So as I was telling you before, I formulate this energy function. So it's basically an energy in the function space, right? In the function space U. But then we need to find the optimal U that minimizes this energy function. And in particular, we are not going to do this for any arbitrary U, but we restrict this to some finite dimensional space. So in this presentation, I consider two neural networks. That is the setting of the physics for neural networks, and polynomials, that is more like kind of a spectral method. So these two kinds of surrogates are parameterized by some parameters theta. That, for example, in the polynomial will be the coefficients that go with the basis. We will see a little bit later in detail that. Or in the neural network will be the learning parameters of the model. And then for optimizing, so for descending toward the minimum, we solve the what is called the gradient flow, and it basically tells us that the rate of change of the parameters is going to be equal to minus the gradient of the loss. And then here it's important to remark that this gradient depends on which metric we choose, which inner product we choose to define the gradient. And then let's say this OD is describing the dynamics of the parameter that when we reach the minimum, if it's just one minimum, and then if the function is convex and it's just one minimum, then this rate of change is going to be 0 in the optimal configuration. And then if we discretize this gradient flow by using explicit Euler, then we recover the standard gradient descent that is known in machine learning. Okay, now, so yeah, so here I want to remark one thing. In the whole setting, we start with our infinite dimensional loss, yes, that is depending on some Sobolev norm, and we need to do two kinds of discretization. So first, we need to discretize the solution itself. What I was saying before, we need to choose a finite dimensional surrogate parameterized by some parameters theta. But we also need to discretize the integral itself. So we are going to present here two kinds of discretization and two ways to discretize this in an optimal way, or the best way possible that we have so far. So as I was saying before, here we consider two kinds of surrogates, the neural networks that correspond to the physics from neural networks methods. And then the main characteristics of pins is that because of the nonlinearities inside the neural networks, this is in general a model that is nonlinear with respect to the parameters theta. The problem of this nonlinearity is that in almost all the cases, or many cases, this will destroy the convexity of the problem. So it means that if our loss is convex with respect to a function u, if I now plug a neural network, then it's not going to be convex anymore. We're going to lose this convexity. And this is a very important property because convexity, for example, guarantees us that we have a unique solution, or even if with a little bit stronger conditions, so lambda convexity, we can prove that we can converge exponentially fast towards the minimum. So with the neural network, we lose this, and then it means that we also lose a lot of the control over the optimization problem. We can also consider linear models, such as polynomials, and here we denote it as polynomial surrogate models, and it's basically, yeah, just choosing some polynomial basis. In most of our applications, we use Chebyshev basis, and then we just formulate the surrogate as the coefficients, theta I, and then the basis, and the sum of all this. Now, the important thing, as I was saying, is a linear model, but linear in the sense that linear with respect to the parameters. It's not linear in the output, so the output is non-linear, of course. If it's a polynomial of more than degree 1, it's going to be non-linear, but it's linear with respect to the parameters. So then this has the property that if our functional is convex, we plug in this kind of surrogate, then the whole discrete functional is going to be still convex. And as I said, this is a property that we really aim for. Okay, now the second part is the discretization of the loss. Here we can consider different kind of discretization, right? So the standard way in which we can discretize a loss is by using the MSE approximation. So we have some randomly distributed points, and then we just consider the mean of the mean square errors. So for example, if you are going to consider the H1 norm, that for those of you who are not so familiar with Sobolev norms, is basically considering the L2 part of the error. So I just have a residual, I consider the square, and I sum the residual evaluated at all the points, the square. And I also consider the derivative to the residual. This is what the H1 norm is. So this is one way in which we can discretize, but in general, this is not the best way to discretize. The convergence rate goes with order 1 over square root of n, and being the number of points. And we can actually do a bit better than that if we have some structure over the training set. This is important to remark. Only if we have the option to choose the structure of the points, then we can get better approximation properties. So this is what we denote here by Sobolev curvatures, and basically what we do is we generalize Gauss legendary quadratures, in which basically you approximate your residual with a Lagrange polynomial, and then integrate exactly this Lagrange polynomial. Yeah? And it gives you a quadrature rule that has much better approximation properties than just summing the squares. And then here we can see a little bit the structure. So at the end, if someone has questions about this, we can go more into detail on what these matrices are. But it's basically the residual time. So it's like a weighted sum of the residual. The W0 considers the L2 part, and the W1 will consider the part of the derivative. Yeah, and then these two things, so the surrogates and the approximation of the integrals is what we're going to consider now for the application. So I'm going to present a little bit of the numerical experiments. We have two papers where we study all these settings. In the first one, that is replacing automatic differentiation by Sobolev curvatures, well, and so on. Here we restrict to surrogates being neural networks, and now we study what happens if we choose just the MSE approximation of the losses, or if we choose the Sobolev curvatures. And in the second paper, we now keep this distinction between standard MSE and Sobolev curvatures, but now we consider what happens when we just choose polynomials, and then you will see what is the big difference of doing this. Now in the second paper, okay, also in the first, we consider different kind of problems. So we consider forward problems, inverse problems, linear and nonlinear PDEs. Yeah. So okay, so let's consider, for example, here the quantum harmonic oscillator inverse problem. So we have the loss, that is basically one term, that is the PDE loss. And here you could see how it would look like with the Sobolev curvatures. So we have these matrices B that are the polynomial differential matrices. So if I apply this matrix to the coefficients of a polynomial, I will be obtaining the derivative of the polynomial. So you have here the whole PDE operator, and this whole PDE depends on a parameter mu that we are interested in estimating. Then we have the L2 norm of this, and we have information of the solution over the domain, not only of the boundary, but over the domain, because now we're in the inverse problem setting. So here we compare different methods. So we compare just standard pins with just the standard MSE loss, and then we can see that in general it does not converge. I mean, the error is 6 in the inferred parameter, and the L1 error. So this is basically, sorry, I need to specify here. Here we're interested in inferring the parameter mu, but also on obtaining the continuous approximation of the solution. And this is what we measure with the epsilon 1 error. How far is the continuous solution towards the analytical one? And then, yeah, we obtain errors 10 to the minus 2, and it takes 1,400 seconds with CPU. Now, the inverse Dirichlet is a method developed by some people in our group, and it basically balances the losses. And you could see how by balancing the losses, by keeping, so we keep the MSE approximation of the error, we keep the neural network part, but now we just balance the losses, and then already the error improves from 10 to the 0 to 10 to the minus 2, and the epsilon 1 error improves also a little bit, 1 order of magnitude. Now, this SC pin is the Sobolev curvature pin, so where we keep the neural network, and now we replace the loss, the MSE loss, by the Sobolev curvature. So we can see that now we obtain 2 orders of magnitudes improvement in the accuracy of the inferred parameter, and also some improvement in the approximation of the continuous model. But the most important thing here to remark is that the times decrease by 1 order of magnitude, so the decrease is already huge. And now, if we go to GF PSM, that is basically the polynomial solved with the gradient flow. So now we keep the Sobolev curvatures and replace the neural network by a polynomial. Then the difference is just huge. I mean, we obtain, how much it is, 7 orders of magnitude improvement in the accuracy, and it takes just 5 seconds. So yeah, I mean, the difference is huge by just doing these 2 changes. We present another example. So now this is the forward problem. Here you can also observe, like we get a huge improvement in accuracy, and it just takes. So here the GF PSM is by solving the problem iteratively. This AD PSM is basically, since in this particular case the PDE is linear, then we can solve it analytically by just inverting matrices, and this is like the limit that you could reach with the method, and it just takes 0.07 seconds. But this is not always possible, right? Because we are not always interested in linear problems. We are also interested in nonlinear ones. So the PSM is more like the reference to look at. Anyways, it's 0.16 seconds, very fast. Now, what happens if we keep constant so we just consider neural networks, and now we study how is the complexity of using the polynomial differentiation, so by using the Sobolev curvatures, or keeping the standard MSE that requires using automatic differentiation. And then we consider here this PDE, which is basically dx to the kth power. So if it's 1, it will be just dx plus dy. 2 will be the Poisson equation, dx squared plus dy squared, and so on, up to order 4. And we compare the runtime from using automatic differentiation against the Sobolev curvatures. And then we can see that the Sobolev curvatures, the complexity, so the runtime remains constant, because basically for computing the first derivative, I have the polynomial differential matrix. For computing the second derivative, I just pre-compute the product of these two matrices, and so on. And for order, will be just pre-computing the fourth differential matrix. But then in the training, I just keep the fourth order differential matrix. I don't need to compute it every time. So the computational time remains constant. But with automatic differentiation, every time we want to compute a further derivative, we need to pass to the whole graph. So then this is scaled exponentially with the order of the operator. And then we can see that at the end, I mean, the difference in the fourth derivative is huge. Yeah. And here I also present the errors. So we are by using the Sobolev QH, we are way faster, and we also remain with better accuracy than with automatic differentiation. So this is again is just by keeping the neural networks as surrogate and just studying what happens if we change the losses. Okay. So a little bit of remarks. The Sobolev curvatures prove to outperform both in runtime and accuracy underpins the complexity with automatic differentiation is exponentially with the order of the derivative. We also have some estimates for this in the paper. And then if we combine Sobolev curvatures with polynomials, then we get this huge accuracy and runtime improvement. But then, I mean, I must say that both the Sobolev curvature pin and the PSMs, they both have this big problem that they suffer from coarse dimensionality and Gibbs phenomena. So coarse dimensionality, because for formulating our surrogate and our losses, we need exponentially many points and coefficients as the dimension increase. And Gibbs phenomena, because polynomials and all these models, they are just good for approximating continuous functions. As soon as we have a discontinuity, then we have the problem that I presented at the beginning. So now, how to overcome at least the Gibbs phenomenon? This is what I will present next. How much time do I have left?
It's okay, go ahead.
Okay. So now let's go into the shock approximation part. So I will present first two problems. First is just approximating a discontinuous function. So no PDE involved, just I have my discontinuous function and I want to approximate it with a model. And the second part will be now how can we extend this into solving PDEs with non-smooth solutions. So we consider a function that belongs on the space of bounded variations. So in particular, in this experiment, we just consider a function that have one discontinuity. It is 1D. If it's 2D, we have, well, it will be a curve. So it could be linear or it could be non-linear. That it will represent, for example, linearly propagating shocks in the case of, for example, the transfer equation with constant velocity. Or you could also have non-linear propagating shocks. We can consider all these kind of cases. And we will consider, so the intuition here, what we will do is we have the discontinuity. We will map the discontinuity to a space where it is continuous, so we kind of stitch together discontinuities. And now this continuous function we will approximate with a polynomial. So we will exploit the approximation properties of the polynomial for the smooth part, and we will resolve the part of the shock. So this is what is more or less written here. We will learn this map phi that maps it to a continuous function and then approximate with a polynomial. And then the great thing of this method is that we are not only being able to approximate this continuous function about the Gibbs phenomena, but we also obtain the parameterization of the shock, which in many cases this might be like the goal that people is searching for. So how do we do this? We basically decompose our hybrid surrogate into parts. The smooth part approximated by a polynomial parameterized by theta, and then the shock will be modeled by the Heaviside function. So it will have two parameters. Well, I mean more than two, but let's say two important parts. The beta, that is the height of the shock, that in general it could be constant, or it could be also depending on time. In this experiment, we consider just that the height is constant, but the position could be changing in time. And the parameter C will be a function of time if we consider, for example, a 2D case where the shock is propagating, or it will be constant, for example, in the 1D case. We just have one point where the continuity is located. So the result will look like this. You will have value of 1 if x is bigger or equal than the curve of the shock, or 0 else. In general, if the shock is non-linearly propagating, so we then approximate again the shock with a polynomial. Now, if we would know the position of the shock, then the problem is solved because we can just stitch together the solution, put a polynomial, approximate it, and then that's the whole problem. But then, of course, in general, we don't know where the shock is located. So therefore, we need to include this into the optimization problem. So in the case of the reconstruction, we will just formulate the loss in equation 13. So we'll have our hybrid surrogate, that is the smooth part, so the Q, that is the polynomial, plus the part of the shock, minus the ground truth, that is a discontinuous function. And then we compute the L2 norm of this. So this is the loss that we are going to minimize. And now we need to infer three parameters: theta, that is the parameters of the polynomial, the position of the shock C, and the height of the shock beta. So in order to compute this in practice, we need to split integrals because how else are we gonna work with the Heaviside function? So let's split the integrals, and from here we compute the gradients of the functional. So one important thing is that this functional is in general not differentiable in the classical sense. So where you get discontinuity, the limit from the left will be different to the limit from the right. So we need to consider kind of different notions of gradients. And in particular, we consider here so we compute the two differential derivatives of the functional that allow us to work with this kind of functionals. And then here just a little bit just to show how is the structure of the gradient. But well, these are not so important. The theta will have a gradient for the parameter theta, a gradient for the parameter beta, and a gradient for the parameter C. That is going to be the one that is a bit tricky. So also another remark is that here we can put explicitly the formulas for the gradients because of the structure of the polynomial. Makes it very easy. Okay, and now let's go to the results. So in this case, we consider a non-linearly propagating shock, no PDE, just a 2D function that has a non-linear discontinuity. And we approximate it with our hybrid model, and then we can see that outside the shock, we are getting errors of 10 to the minus 6, which is pretty good. It's almost the limit of what the polynomial can approximate. And then at the shock, we still have some errors that corresponds to the fact that we are not resolving exactly the position of the shock, but it's within a band. That depends on the training set we choose. But the important thing is that in this setting, we are not getting Gibbs phenomena. So as we can see here, this is just the comparison between the PSM. Well, here is not PSM, is the hybrid model. I forgot to change this. And against the ground truth. So we can see there's no oscillations now, as I presented at the beginning. And we compare this hybrid surrogate with just normal neural networks with ReLU activation functions and normal neural networks with time activation functions. Then we can see that the polynomial has better accuracy, 2 orders of magnitude better, and the runtime is also faster. And here in the second plot, we can see what happens if we compare the profiles. So this is just a cut to the function. If we consider the cut, what happens with the other surrogates? So the interesting thing for me at least when I saw this result is that the sign also presented this phenomena. So then this means that it's not only a matter of choosing neural network, but which activation function and which approximation property you have for this neural network. And then the ReLU performs a bit better. We don't have the Gibbs phenomena, but then I don't know if you could see here a bit. There are some non-smoothness that comes from the ReLU. And this will be a big problem when we go to PDE setting because in general ReLUs are not differentiable. So they're continuous but not differentiable. So this might be a problem we want to solve PDEs. And then I mentioned here that the limit case of the method is 1 to the minus 8, because if we would know exactly where is the position of the shock, we will obtain errors of 10 to the minus 8. But then, of course, I mean, in practice, we also need to estimate the shock. So this is just like the limit that we could reach. Now we go to the PDE setting. So let's consider now the transport equation. We just deal the boundary condition. The velocity here is constant. And then we want just to propagate a discontinuous function. Now the problem is that here we cannot just compute the derivative, because what is the derivative of the heavy side? And then in particular, this function is not classically differentiable and is not weakly differentiable. So we can also not define weak derivatives, as for example in the finite element setting. So here we need to work with the notion of distributional derivatives. And more or less the intuition is that the derivative of the heavy side will be a Dirac, right? It will be more or less infinity at that point and then 0 side. And in particular, it's a measure. So the effect, in practice, the effect of this is that we will have our PDE. We test it with some test functions that for us is going to be again Lagrange polynomial, and then we will obtain that the derivative tested with the smooth function is going to be the test function at the position of the shock. And with this, we are going to obtain the parametrization of the. So we'll obtain inside the loss the effect of the shock. And now we, as before, we formulate the loss with the PDE term, we formulate the loss with the boundary condition, and so on. We formulate all these gradients, and now we optimize again for the size of the shock, the position, and the parameters theta that solve the PDE. And this is just a preliminary result. I mean, there is a lot more to improve in this setting, but at least we can see that we don't have the Gibbs phenomenon. And we can solve the transfer equation for a discontinuous function. We can propagate a non-smooth solution. And then the limit case in this setting is 1 to the minus 8, if we would know where the shock is located. So yeah, so a little bit of the future work, just to mention. I mean, we can discuss maybe in this discussion part. So basically, one of the big problems for computing all this approach is that we need to check in which side of the shock are the training points located. And right now we are doing it naively by just every epoch we check all the set. Is it at the left or at the right at the current iteration of the shock? But we can maybe improve this if instead of just checking all the training set, we just check the set that is within the band of evolution. So I mean that if we have first a shock at this position and now it evolves a little bit here, we'll have like a region of points that were before at the left and now they are at the right. And then we try to check this condition by using cell list or bed list, like in the particle method setting. And this should improve the complexity a lot and reduce the runtime furthermore. So the second project that we are thinking on start working is trying to solve PDEs with topological defects, so including the singularities with this structure of the shocks. The third one is now what happens if my shock is not a function like this, but now it's, for example, a closed surface. So how can we still get like this decomposition? And then basically the idea is to replace here the C by an implicit representation of a level set surface, and then just do the same approach. And the last part is how to improve the optimization that will allow us to reach like this limit case that I was saying before. And it's basically one thing that we are trying right now is many of the functionals when dealing with the shocks, many of the terms are nonlinear with respect to the shock parameters. So the PDE is linear itself, but if you see the parameter is inside, for example, the test function, and this test function is nonlinear. So we are now trying an approach which is basically linearize the functional and then doing implicit time steps in the linearized direction. And this has already shown some improvements in the method. So yeah, I guess with that I would like to finish. And yeah, I'm happy to answer questions.
Thank you, Juan. So I'm opening the discussion. Whoever wants to ask a question, please raise your hand. I have several. So let me start maybe. Juan, I'm not sure if I got correctly the procedure. Let's say, can we go to page 12, for instance? Right, you have the runtime here, right, in the table. And what's the runtime? The prediction or the training?
No,
runtime?
the training. The training.
The training runtime. And okay, so can you compare the efficiency with respect to the prediction?
To the prediction.
Time?
So in the three first methods, it's going to be the same because we are using the same neural network. So the complexity will be just the complexity of evaluating the neural network. And then for the polynomial, I will expect it much less because you have less parameters and less bases. But it depends also on which basis you choose. Yeah, but the first two methods will have the same cost of predicting.
All right. And what is the neural network that you've been using? What's the architecture? Because
It's just
I mean,
fully connected, 4 layers, 50 neurons each.
right, but if it's 15 neurons each layer, you mean?
Each layer, yeah.
Okay, so you haven't increased the number of neurons in the latent, in the hidden layers, because this is something that can bring some more nonlinearities to your model.
It could be that it brings more nonlinearities and maybe the approximation error improves. But for sure, the runtime will increase furthermore, right? For computed derivatives and so on. If you increase the number of layers and neurons, then the cost will be higher.
And what was your training procedure? This was supervised or unsupervised learning, because you had the physics informed loss function, so probably you could count on some unsupervised learning procedure. But what was your training procedure?
So in this setting, I mean, at least for me, maybe you will correct me, but for me, unsupervised would be the forward setting, where you impose boundary conditions, but you just have information of the boundaries, and you have the PDE, but you don't have information of the solution over the domain. For me, this will be unsupervised, kind of, and the inverse problem will be supervised because you need information of the solution over the domain. The point is that for the forward problem, I'm not sure that you can solve it without the boundary conditions, because then it will not be well posed. So you don't know which solution you will converge. I don't know if this is what you mean, or is there any other kind of unsupervised setting for this?
So I mean, you had some training data, right? Or for the supervised training. So what was the size of the data set? Or how did you choose the sampling points if it was unsupervised?
So again, in the inverse problem, I do have information of the solution over the domain. In the forward, I just have it over the boundaries. And then the training set for the pins, for the pin and ID pin is just randomly sample points, and for the SE pin and the PSM is legendary grids.
And how did you choose the training points? I mean, the inputs. How did you choose it?
So in the SE pin and PSM, it's just the legendary grid. This is a fixed grid that depends on the degree of your polynomial. I don't know if it's clear. I mean, that's what I was saying before. We are exploiting this structure of the points to formulate all these differential operators and so on. But we choose which training points we use. And on the legendary grid is just the zeros of the nth degree legendary polynomial. So it's just a grid with some structure. In the pin and ID pin is more like randomly distributed points.
What I mean is, for different boundary conditions, you would expect different solutions, right?
Yes.
So, and the question is, how did you choose the boundary conditions for your training?
Okay, got it. So in most of the examples we present, it's just one boundary condition, But actually, we have done experiments. I don't have the plot here, but we have done experiments in which, for example, you train it for one boundary condition, obtain one solution, obtain it for another boundary condition, obtain one solution, and so on. And then you are interested in obtaining the continuous model across boundary conditions, right? So for any value of boundary condition within a range, what is the solution? And this um, we have also done it before, and also presents very good approximation properties. So you can just obtain the continuous model also along the boundary conditions direction, let's say, or parameter. For example, if we choose a different mu in the forward problem, I can also, so let's say I solve the problem for mu equals 0, mu equals 0.5, mu equals, I don't know, 1. Then I can also obtain values in between these parameters.
But you have 3 different neural networks or 3 different models then, or a single model that combines the information?
It will be a single, I have done it with the polynomials, and it will be just a polynomial. Let's say the test I did was in 1D PDEs. So you will have 1D, and then in the second direction, you will have the parameter. And then you will have a 2D polynomial telling you what is the solution in the intermediate point. If you have another parameter, then it will be 3D for the.
I see. So using the fact that no one is asking question, may I ask you another one about
Yes,
the automatic differentiation that you have there? So how is it involved there? I mean, what sort of function AD is playing in your formulation, and what sort of AD formulation do you use? In particular, do you use some reverse mode of automatic differentiation or the forward mode? Because it's, I mean, depending on the type of AD that you use, the efficiency can be affected.
Yes.
For instance, in the TensorFlow, there is the reverse mode that is available. But the question is to you, how do you use the AD, and which, let's say, option or version do you use?
Yeah, I think we use reverse mode. I'm not entirely sure. But the way in which the derivative enters is here. So for example, we compute the MSE approximation of the loss. So we need to compute, for example, special derivatives for the residual. This special derivative in the setting of the pin and the ID pin in these two methods, this is computed via automatic differentiation. In the case of Sobolev curvatures and the PSM, we don't need to use automatic differentiation. So we replace entirely the automatic differentiation by the polynomial differentiation. This is where they are involved.
I see. Jack, I can see that you wanted to ask a question.
Hi, Juan. That was a nice talk. I came in late, so I didn't see everything that you showed, so I'm sorry if I ask a silly question. What are the limitations of using the Sobolev cubature? Are you limited to kind of tensor product domains? What are the limitations there in terms of solving PDEs on general domains?
Yeah, so this is a very good question. There is one concept that is the LLP degree of the polynomial. So for building the quadratures, we are always referring to some polynomial that will tell us, for example, the points and the weights of the quadrature. If we are choosing L infinity degree, then this is just tensorial product of, let's say, if we are in 2D, we choose the 1D points in each direction, and we do tensorial product. And this is why the scale exponentially with dimension. So this is the first limitation, right? The dimension cannot be too high because then it will explode. But then you can relax a little bit this, and then you can choose, for example, a degree L2. That basically considers less monomials, and then your grid will be, let's say, smaller. And this scales, so the number of coefficients for the polynomial will scale to the exponential. And now if you choose L1, I think this scales like polynomial. So there are ways to kind of mitigate it, but it's not the complete solution.
Yeah, I see.
And then the second big problem is that in this setting we need within structured grids. So one of the directions in which I want to go, I don't know, a couple of minutes, is building same kind of approach, but now for unstructured grids, so just any arbitrary grid. And this I'm planning to do with maybe DCPSC operators or RBF, but having the same thing, you compute everything on the loss and you keep this decoupled from the surrogate.
Mm-hmm.
Yeah.
Yeah, so I had another question. Here you have the runtime, but I was also interested in the scalability of the method. So if you double the problem size, how does the runtime change?
Yeah, this is a good question. I don't have these plots here.
Because that would be my I think, when you show runtimes, and especially when you go to review, my experience is that you can have trouble, the kind of troubles that Jakob mentioned, right? People can be quite, how did you implement it? Could you change this and that? And I think if you look at scalability, you're not looking necessarily at just the run, it's more persuasive your argument if you look at scalability than pure runtime alone.
Sure. You're right. And this is something that actually, I'm missing to compute. You're right. There's one problem though with the scalability of the method, and it goes again to the whole difficulties that this self-constrained formulation presents, and is that it can be that your runtime, increasing some amount, and your accuracy should get better because you can prove, for example, that the polynomial will converge as the degree increase and the quadrature will converge as the degree increase. But that doesn't mean that optimization problem will remain the same as you scale the system. So it can be that with one particular configuration, you converge and you obtain amazing results. But now if you increase the degree and if you increase the points, then maybe you have problem convergence. And the same with neural networks, with just the standard pin. If you try to scale it, we don't have that much control over the optimization part.
Yeah.
So it is let's say not so trivial, but it's true that this will be very interesting to see.
Thank you. Good answers. Thanks.
Juan, I have a question about the solution procedure, because in fact, I'm not sure if I understood correctly, but you pose a problem for a given boundary conditions and a given domain, and you use different approaches to actually solve the problem, right? Yeah. It is not fitting the surrogate model, but solving a problem, approximately solving the problem with different approaches. Is it true?
This is correct, exactly. So at the end we obtain the parameter. Sorry.
Just to finalize my question, so the runtime corresponds to the solution procedure of a given problem, and for the pins, for instance, neural network-based pins, you use the gradient-based, the standard optimizer that is probably used in some library for the neural networks. And for this GF PSM, you mentioned that you are solving the system of equations, right? So it is a direct or iterative method to solving the system of equations, which may be even a second order, like the Newton method, Newton-Raphson, for the nonlinear problem. So how can you compare the timings then? If you use the different solution methods, if you want to compare the different approximations, but you use a different solution procedures, this can be affected by the choice of the solution procedure, the runtime, the solution time. So can you, let's say, clarify this? Because probably my question is because I didn't understand it fully, what you are doing, but if you could elaborate on that.
Sure. Also very, very nice question. It involves like a lot. So the optimization algorithm that we use for pin, ID pin, and SC pin is the same. I fixed that, right? To exactly be able to compare the runtimes. For the GFPSM, we have also experiments in the paper with LBFGS optimizer. And this is where the GFPSM part comes in, and the AD PSM part is where we solve actually the linear system. And this is what I was saying, that this is the limit. Because just in the linear case, you can solve these things with LSTSQ, for example, and then you will obtain the best accuracy. But then, of course, not realistic, because we are interested in general for iterative algorithms. So yeah, in the paper, we also compare with just commercial optimizers, the PSM.
I see.
The main thing here of why the runtimes make sense, and it's not just a matter of the choice of the optimizer or the model itself, is precisely the complexity of the problem, right? So first, the PSM has less parameters. So if we choose, for example, a polynomial of degree 100, which is already very high, so we can capture very high oscillatory functions. The number of parameters will be much less than the ones that we are using for the neural network. So this is the cardinality of the training parameter is smaller. And second, the whole problem is convex. So then you can prove, we also have it in the paper, you can prove that this converges exponentially fast, right? Because you just have one minimum, you will very quickly go to this minimum. The neural networks have to deal with a lot of local minima maybe, and this is why it's important also to use this Adam optimizer and so on. If I try to use Newton or, I don't know, explicit Euler for solving this with pins, it will explode, it will be unstable. With the PSM, we have this very nice structure that we can exploit and obtain this fast approximation. So it's, we can also argue this theoretically, the rates and the approximation properties.
Can I ask another question?
Yeah, sure.
So the polynomial approximation you use, is it from this paper from Hecht in 2020? Is that?
Yeah, I mean, yes, it's based on that, but I mean, there he explored this problem of the LP degree of the polynomial and how to uniquely determine these polynomials with some unisolvent nodes. Here is just basically using, for us in this setting, is using spectral methods. I mean, just Cherry-check polynomials for the surrogate and Lagrange basis for the quadrature. So this is just a standard polynomial.
Okay, because it was a little while since I read that paper. My memory is that the kind of core feature of that paper is that the Chebyshev approximation doesn't scale to high dimensions, right? So they have a method which scales to high dimensions. And I was also thinking with your work that one kind of thing that would be very convincing is if you start looking at high dimensional PDEs, because they're things which are really tricky to solve with classic methods like finite element methods and PDEs in 5, 6, 7 dimensions. Because I think you're just looking at 2D, but I'm saying if you use the polynomial approximations they proposed, you could maybe go to a higher dimension setting. And that would be
definitely.
Cool.
This is true. I mean, I don't know if you are seeing here, Hecht is my supervisor.
Yeah, okay.
So this is something that we have in mind for sure. And this is what I was saying, that the LP degree could make this scale much better. The problem is that in the quadratures, you cannot survive this course of dimensionality. So in the model itself, yes, but the quadrature, no. So this is why we need to search other alternatives. And this is why I'm saying that this kind of RBF basis or the SPH basis could maybe offer a solution for this dimensionality problem. So the logic with this kind of a structured basis is that you will reduce a lot the accuracy, it's still better than MSE, and still you will guarantee some polynomial rate of convergence. This is like what I am targeting to. Yeah, but let's say work in progress. And also another distinction is that in the paper of Michael, he does all this for interpolation. Here we're solving the regression problem.
Using the interpolation of the PDE. Yeah.
So this is more like the regression problem.
Yeah, it's true.
Yeah.
Thanks. Interesting.
Okay, so I can see no more question, and let me thank again to you, Juan, for the presentation and for answering our question, and thank you all for the attention. We had a bit of discussion as well. Have a good day, and I will keep you posted about the future seminars. Goodbye.
Thank you very much. And any questions, just feel free to write an email, and I will share the papers and results and so on.
Sure. Thank you.
Thank you. Bye.
Bye bye.